Hello everybody, my name is Mr. Lakin. I'm going to be doing the first two lessons for this set of videos for all the different derivative rules that you're going to need to do. You should have your packet out. You're going to be on this page that's lesson 2.2, rules for differentiation. And you can see there that by the end of the lesson you should be able to apply all these different types of rules. And it will be over the course of a couple of days that you should really be able to accomplish this. There is a note at the bottom of one of the pages that says notation reminders. We're going to take care of this at the end, just for the sake of time. So please go to the next page. There's going to be all these shortcut rules for differentiation, and you may remember that the derivative was given to us by this form, f the limit as h approaches 0, of f of x plus h minus f of x over h. And the whole point of these rules is that we want to kind of make our lives a little bit easier, that all of these rules will just be, there'll be a shortcut, in other words. We won't have to continuously use the limits over and over and over again. Now, in a way, it's a blessing because it's gonna make your life a little bit easier, and it will be less difficult notation to use. The flip side, though, is that you're gonna start losing your fun-filled existence because there's going to be a lot of rules to remember, and there's also going to be a lot of moments where you're not sure which rule goes when. So that's going to be the difficult part of it. For now, take a look at the first one, the constant rule. It says d dx of c equals what? If I have a function that's a constant, so we'll call this line the constant, and I'm looking for the slope of its line, well, we know that the slope of a horizontal line is 0, which means the derivative of any constant c, no matter where its function lies, will always be 0. That was an easy one. The next one, the power rule of d dx of x to the n. This is called the power rule, and we've proven it once in the local linearization packet. And if you don't remember it, basically the n comes down as a coefficient for x, and then we drop the exponent, the original exponent, by 1. And there will be examples with how to do these. The next one is the constant multiple rule. Basically what this is saying is that if I have some coefficient of my function, what I can do is just rewrite this as the coefficient times the derivative of x to the n. And what that's equal to, again, we just said that this is the power rule. So the power will drop to the front, the original power will drop to the front, and the new exponent will be here. And this is my answer. The whole point of the constant multiple rule is to realize that when you have a coefficient of a function, it just ends up multiplying whatever was left over from the derivative. Finally, the derivative of an addition or subtraction, a sum or difference, this can be broken up as such. Derivative f of x plus, if you're adding, or minus, if you're subtracting, the derivative of g of x. Please pause the video now to try these, and then when you're all done, unpause, and I will show you the answers to these, and then we'll go over notation afterwards. So please pause the video now. So for the first problem, d dx of x to the 8th, this is the power rule, so what I have to do is I have to bring the 8 down in front. X stays there, and now it's going to be the original exponent minus 1, which will now be a 7. That's it, that's your answer. For the second one, it's d dx of 1 over x to the 4th. Now this one's a little bit trickier because you want to bring the 4 down here, but how does it really work? We need to rewrite this. And I spelled rewrite wrong, unfortunately. That's embarrassing a little bit. And what I'm going to do is I'm going to rewrite this as d dx of x to the negative 4. because that's really what 1 over x to the fourth is. It's its reciprocal. Seeing x to the negative 4 in this form, it's now more apparent for the power rule to be used. So I'll perform the power rule now. The negative 4 comes down in front, and the original exponent drops by 1, which means it's going to be x to the negative 5. Now be careful on this one, because it is tempting to say negative 3, but that would be a n plus 1 instead of an n minus 1, as the power rule says. The AP test may not exactly have the answer that you have originally, so you may have to rewrite it, and both answers here are going to be fine. You could also say that the answer is going to be negative 4 over x to the fifth. Either answer again would be fine. As we continue our practice with derivatives, we will want to take our time to make sure that we are aware of how we can rewrite our answers, because the multiple choice portion will not be so friendly and provide us the first answer that we come up with all the time. So for the next one, d dx of 4 root x, the fourth root of x. Again, this is another power rule, but it's not really apparent as to why yet, so we will need to rewrite. And I'm going to rewrite this as d dx of x to the 1/4. The fourth root of x and x to the 1/4, those are both equivalent. And I'll give a general rule, a general way to remember when to use the power rule after this. So we have d dx of x to the 1/4. The 1/4 will drop down, and then this original exponent will be subtracted by 1. So we have 1/4 x to the negative 3/4, which is our answer. And you could rewrite this, but this is kind of a little bit more cumbersome notation though. And you're less likely to see this bottom choice as an answer on an AP exam. But as said before, both are equivalent and both are correct. I hope you didn't have too much problems with x squared minus 2x minus 3. This is the sum and difference rule. I just take the derivative of each term. So the derivative of x squared will be 2x to the first. The derivative of negative 2x will be negative 2. It's technically x to the 0, but x to the 0 is 1. So it's negative 2 times 1, which gives me negative 2. The final one is the derivative of negative 3, and that's just 0. So we do have a plus 0 here, which I won't take the time to add, and our answer is 2x minus 2. Our final problem. We have d dx of pi divided by 3x squared. The first thing that I'm going to do is I'm just going to rewrite this as pi over 9x squared. The second thing I'm going to do, this pi is not really doing anything. It has no bearing on x squared really. It's a coefficient in other words. Similarly, this 9 is doing the same thing. Pi over 9 is a coefficient for 1 over x squared. So I'm going to rewrite this as pi over 9 d dx of 1 over x squared. Now you may remember from the above example that 1 over x squared could be rewritten as a function with just one exponent and not as a fraction. And what I mean by that is we can have pi over 9 times d dx of x to the negative 2. 1 over x squared being equivalent to x to the negative 2. This is a big key that I'm going to be using my power rule here. So I'll have pi over 9 times negative 2 x to the negative 3. Again, we are subtracting 1 from negative 2, not adding, so our resulting new exponent is negative 3. If we'd like, we could rewrite this answer as negative 2 pi over 9 x to the third. Both answers were correct originally, and both answers are equivalent. So this is all for the examples for the following rules, which were constant rule, power rule, constant multiple, and sum or difference. Now I did say that we would return back to the notation reminder, so we'll go ahead and do that now. Originally we said that the limit as h approaches 0 of f of x plus h minus f of x over h is equal to the derivative, the slope, of f at any point x. Since we're going to be doing some shortcuts now, some derivative shortcuts for not only this portion of the unit but for the remainder of the year, I want to make sure that we're clear on some notation because you're not going to always see f prime of x. So what I'm going to do is I'm going to make a chart, and for this first line I'll put d dx. I'm also going to put d2 dx squared, and this is going to be the most popular notation that we'll see. For this first one, we say this as the derivative of f of x with respect to x. For the second one, again, I know the notation looks very strange. We just say, we repeat everything, but we say for the beginning the second derivative. Or in other words, the derivative of the derivative. This notation is called Leibniz notation, named for a famous mathematician, Gottfried Wilhelm Leibniz of the 17th century. The second most popular notation you're going to see is f prime of x. Again, the way we say this, we say f prime of x, and this is called prime notation. It's also called Lagrange notation for a famous mathematician, Joseph Louis Lagrange. These are the two major types of derivative notation you'll see on the AP test. They're the only two types of derivative notation you'll see. If you go to multivariable calculus, though, you will see this notation. By the way, we say this notation is d sub x of f of x, because there is an f of x here for both. This is operator notation, also known as Euler notation, for derivatives. So I label the top of the rows here. The first one is the notation. The first left column is notation, the middle column is how to say it, and the third column is the name of the notation. You'll never be tested on the name of the notation, but you'll want to be familiar with it. You will have to be responsible for knowing the different types of notation, how to use them and how to write them, though. And of course, you will want to know how to say them to communicate with anyone else in the class. Finally, the last thing I'll say about the notation is there are pros and cons for each one, and I think you'll find the pros and cons throughout the remainder of the class. Other than that, that's it. Thanks for watching the video.